So as we transition into the back side of the worksheet, we're going to take a look at a problem from your textbook 10.7b. And what we're going to do today is we're going to set up a one sample z-interval for means. Yesterday we talked about the formula, but usually when you construct a confidence interval, there's a few additional things that you want to include as well. So a reminder from yesterday, we're going to use a one sample z-interval for means to predict mu, the population mean, when we know the population standard deviation. In reality, it's unlikely that you're ever probably going to use this confidence interval in real life because chances are if we don't know what mu is, we probably don't know what sigma is either. They're both population values, so if we know one, we probably know the other. However, because this is such an easy model to work with, it's usually a nice one that we start with in introductory statistics. So the problem we're going to solve is problem 10.7b. You'll find this on page 549 in your book. And you'll notice on your homework calendar there are some problems where it says you're going to be solving problems the long way, and this is going to be such a problem we're going to work with. So let me introduce you to this problem. Here are measurements in millimeters of a critical dimension on a sample of auto engine crankshafts. The data come from a production process that is known to have standard deviation sigma equals 0.060 millimeters. The process mean is supposed to be mu equals 224 millimeters, but can drift away from this target during production. We're going to do part B, which says give a 95% confidence interval for the process mean at the time these crankshafts were produced. So let's get started. We will eventually substitute the values in the formula to come up with an answer, but when you do a confidence interval on an AP exam, there's a few other expectations. I've narrowed it down to 4 particular steps, and in step 1, you're usually asked to identify the name of the procedure you're using, the parameter you're estimating, and who the population is. 3 P's, PPP. Because in the problem they tell us sigma, the population standard deviation, we're going to be using a one sample z-interval for means. You don't have to write this as a complete sentence. In fact, you can just say one sample z-interval if you want to. The parameter in this population is what we're trying to predict, and it's mu. In fact, for the first few confidence intervals we're working with, we're always going to state what mu is. What does mu stand for? Mu is the mean. The mean what? Let's go back to the problem. In the problem, there's a few places where they talk about mean. You'll see it talks about the process mean here, talks about the process mean here. It's not a lot to go with, but it's all we've got. In this case, mu is the process mean. Now we address who the population is. I think the easy thing to find is the sample first. So let's go back to the problem. It says in the first sentence that we're taking a sample of auto engine crankshafts. So if our sample are these auto engine crankshafts, the population must be all auto engine crankshafts. So that's step 1. We've named our procedure one sample z-interval because we know what sigma is. We introduced our parameter, which for right now is always going to be mu. Mu is a mean. What kind of mean? In this case, it's a process mean. And our population is all auto engine crankshafts. Step 2, check conditions. In real life, if you're using this type of confidence interval, there are 2 conditions that need to be met in order for you to legally use this interval. The first condition is that data is taken from a random sample. This is important because if we take data from a random sample, this reduces bias. The second condition is that your population distribution is normally distributed. Now there's 3 ways to verify this condition. If the problem actually says the population is normally distributed, we're good to go. If the sample size is large, this infers that the sampling distribution of the sample mean is approximately normal. Those graphs that we have on the board, as the sample size increases, our sampling distribution is approximately normal. That's a way to get normality. If these 2 things don't work, then try step C, which is graph the sample data and show that the sample is approximately normal or symmetric. So in our problem, let's take a look at what it says. So in our problem, it talks about a sample of auto engine crankshafts, but as I read through this, it doesn't say anything about random or SRS. So if that's the case, we really don't have this first condition met. What do we say if a condition isn't met? We're going to say it does not say a random sample was taken. Maybe it was, maybe it wasn't. It doesn't say. If it was not taken, we're going to say we proceed with caution. We're not actually going to stop doing this problem. We aren't sure if a random sample was taken or not, but we're going to let the reader know that just kind of be careful with our information here. Even if a condition is not met, we're just going to address the fact that it doesn't seem to be met, proceed with caution. In real life, we'd want to make sure it's random. In AP statistics, we're just going to keep on moving. Second step, does it say anything about normal in the problem? In step A, which we didn't read, it actually says we expect the distribution of the dimension to be close to normal. If you read that and caught that, you can actually use that for a rationale saying, yes, that condition is met. Now, the problem didn't actually say the population is normally distributed, but it did drop the word normal. It is fine to actually plagiarize the exact same sentence it says in your book. So if the book says we expect the distribution of the dimension to be close to normal, you can actually write that, and it's okay on the AP exam to actually say that. But what if you missed that line in part A? Because we were just supposed to do part B. What could you do if you actually missed that? If you missed where it said normal, we could also say if the sample size is large, then we could continue to proceed. We don't have a large sample size here. If you count the number of engine crankshafts, we have 2, 4, 6, 8, 10, 12, 14, 15, 16 of them. In order for there to be a large sample size, we need to have at least 30. 30 is considered to be the breaking point between large or not, so we don't have that. Option 3 is we can actually graph the sample data and determine if this data is approximately normal. So one option that you have is to actually type these numbers in your calculator and observe the graph. Once you've entered all these numbers in your calculator, we can go to second y equals the stat plot. And there's a graph that we talked about in chapter 2 called a normal probability plot, which we'll actually use here. So after you go to second y equals, make sure one of the plots says on. And we're going to choose the last type that's listed here. So scroll all the way to the right till this last one is highlighted. If your data is in list 1, make sure that's your data list. We're going to set the data axis to X, and our mark, I like to use a square. And we're going to do zoom 9 to fit a nice window to this data. And when you do zoom 9, we get a graph that looks like this. Back in chapter 2, we had said that if this data is approximately linear, then it's reasonable to assume that our sample data is approximately normal. And this graph here, it's not great, but I do kind of see an outline of a line. It's not outstanding, but we're going to consider it good enough. So if you missed the part that talked about the distribution is close to normal, what you could also say is this. The normal probability plot, so name the graph, the normal probability plot is approximately linear. So it is not unreasonable to assume that the population is approximately normal. In other words, since our sample data looks pretty normal, it's probably a good chance the population data is too. Why the big words? Because that's what the graders on the AP exam use in their grading rubric, so we're going to follow what they use. Mr. Herrick, I don't know if I can remember this. Why, sure you can. Heck, you could even write a song about it. The normal probability plot is approximate linear, so it is not unreasonable to assume that the population is approximately normal. So again, for checking conditions, you need to talk about the random sample part. Doesn't say it was taken, so proceed with caution. And then this normal distribution part. If you copy down this thing that says close to normal, that's all you have to do. In some problems, it will say normal, so you can just copy it down. If not, check to see if the sample size is large. If it is, you can use that. If that's not the case, graph the data. There's never been a problem on an AP exam where at least one of these conditions you can't check. Step 3. This is where we actually carry out the procedure and calculate what we did the other day, which is X bar is our sample mean. In our data, we can calculate the sample mean by using one var stat. So using the numbers that were already in my calculator, I can do stat, calc, one var stats with list 1, and you'll get what X bar is, which is this number. Don't round it yet. For Z star in this problem, it says we're using a 95% confidence interval. So again, we can go to our table, look up 95% confidence and our bottom row value, and we see again it's 1.960. For sigma in this problem, be careful. They do give you a value for sigma. Sigma in this problem was equal to 0.060. Do not use the value from the calculator, which a lot of times is close. Granted, here it's not that much different, but sometimes the calculator will give you something different. If they give you a sigma in the problem, use that. Never use the sigma value from your calculator. So we are going to use just flat out 0.060. Do not use 0.0598 here. In your denominator, we have n, and as the sample size, your calculator will tell you this as well. It's 16. Then we can calculate what this is equal to by substituting these numbers into your calculator. And the first value we got was 223.973. I go back to my calculator and type in second enter and replace the minus sign with a plus sign to get my second answer, which is 224.031. In step 4, we interpret the results, which is going to be using the first of the 3 interpretations we used on the front side as a model. So you might remember on the front side of the worksheet we said we are 95% confident that the mean year is between 1979 and 1998. We're going to use our percentage for this problem, 95%, but we're going to replace what the mean is and obviously what these last 2 numbers are. So our conclusion will always look something like this, and it's a lot of fill in the blanks. We are, fill in the blank, 95% confident that the mean, now in our problem it's not a mean year, it's a process mean. So I'm going to kind of plagiarize a little bit from up here. We're 95% confident that the process mean and if you want to say for all automobile crankshafts, you can do that. We are 95% confident that the, restate what the mean is between the 2 numbers that you got, 223.973 and 224.031. If there's units in the problem, it's good to include those as well. In our problem, the units are millimeters. So on your homework assignments, there's sort of 2 different ways that you'll answer a confidence interval problem. If the problem says complete the problem using the short way, all that means is use step 3. Carry out the procedure, plug in the numbers, get an answer. If the problem says long way, the expectation is that you're going to show the 4 steps like we addressed here on the back side of the worksheet. We're going to practice this an awful lot this unit, and you're going to actually get pretty good at this along the way.